Hey class, this is Ms. Roberts at Shasta High School, and I'm going to be going through the chapter 3 study team test. Unfortunately, I didn't change this number, so this is a little misleading, but this is indeed the chapter 3 study team test that we took last week, and we're going to go through these questions. So first question we have right here, question 1, gave us several monomials, and we were asked to simplify them. Let me hide me. So on this first one, right, I have something that's being raised to the third power, something to the third power. Well, conceptually, I understand that if I'm raising something to the third power, I have 3 copies of this. So what I can choose to do, one of the things I could say, hey, this is a 3x to the negative second times another one, right? So that's one way for me to think about this, to expand it. Another way I can think about it is if I have this idea of a power raised to a power. So for example, if I have x and I raise that to the m power, right, and then raise that to the n power, that's the same as x to the m times n power. And you can see that that's happening here because if I take the 3 and I multiply it by the negative 2, there's my 3 times the negative 2. This becomes x to the negative 6th power. And also I've got this 3, right, that's being 3 to the first, and that's being raised to the third. So that would be times 3 to the third power. Okay, so not done, right? But 3 to the third is 3 times 3 is 9 times 3 is 27. So I've got 27 times x to the negative 6th power. And then as a final step, right, we're not writing our final answers with negative exponents. This x is being raised to the negative 6th power. So I know that this is equivalent to, again, there's a 27 in the numerator still, and then there's an x to the positive 6th in the denominator. That 27 is not being raised to the negative 6th. If it was, it would be much larger than 27 at the end. It's just 27. It's the x that was being raised to the negative 6th, and that's why that's pushed into the denominator. So this is our answer here. This is 27 times x, 27 over, rather, x to the 6th power. Let's look at B. So on B, right, part of this is I've got a 5 over 15. And I understand from a long time ago that that's the same as 5 over 5 times 3. So I can see that there's a giant 1 here. It doesn't become the number 3, right? There's a giant 1 that's in the numerator. So there's a 1 in the numerator and a 3 in the denominator. So in terms of the 5 and the over 15, that's 1/3. But then we've got to deal with this negative a to the negative 5th. Certainly, one of the things I can do is I can just say, hey, this is a to the negative 5th. I'm going to move this into my numerator. So this is going to become what? I've got an a already in the numerator times a to the positive 5th, right? Which is going to give me what? It's going to give me a to the 6th power. Another way to think about that is I have a quotient here. I have the same basis, like this is a to the 1st over a to the negative 5th. That's the same as a to the positive 1. That's what's in the numerator. A to the positive 1 minus a negative 5, which still gives me the a to the 6th, right? So it's going to take a while till we're comfortable and we look at these and we know what they are, but a over a to the negative 5th is just a to the positive 6th. So I've got an a to the 6th that lives in the numerator and a 3 that lives in the denominator. So my final answer is a to the 6th was up in the numerator, and there's a 3 in the denominator. So a to the 6th over 3. Those were the two that were most often missed. Let's look at part C. Not missed, except for a couple people decided that they saw this as multiple terms. There's no terms here. These are just all factors. There's no plus or minus. There's not things being added or subtracted. So 4 times 3, I can associate that, do that multiplication. 4 times 3 is 12. And then if I have an x to the second, that's 2 factors of x times x to the 5th, 1, 2, 3, 4, 5. That's going to be x to the 7th power. So that's what C was, 12x to the 7th power. And the last one there is D. D in my denominator, I'm just going to go ahead and expand this out. I've got an x to the 7th that lives in the numerator. In my denominator, I have 2 of these 2x to the 4th. So I can write this as 2x to the 4th times another 2x to the 4th. So in my denominator, I'm just going to rewrite my numerator, x to the 7th. I've got 2 times 2, which is 4x to the 8th. And I think we know how to deal with this, right? If I've got x to the 7th over x to the 8th, that's the same as this, right? X to the 8th is x to the 7th times x to the 1st, right? And then you can see there is a giant 1. So I'm left with just a single factor of x that's in the denominator, and I also had a single factor of 4 that was in the denominator. So what do I have? In the numerator, I have the number 1, and the denominator, there is a 4, and there's an x. Okay, next. It says, solve, it's recommended that you verify your solution is, it's recommended that you verify that your answer is indeed a solution. Let's take a look at this one. So first thing I'm going to do is use this thing that we call the simplest form of the distributive property, and I'm going to rewrite the left-hand side. So I'm going to have here a 3x plus a 5 plus, here's a rewrite, 2x minus the number 12. Why did I write 16? I don't know. 2x minus the number 12. That's better. And you can see I just multiplied 2 times each of these terms, right? There was a term of x and a term of -6, and that's what I get. On the other side, I've got 3, and again, I'm going to use the simplest form of the thing we call the distributive property, 3 minus 4x, and then minus the number 4. Okay. I'm going to collect like terms on the left-hand side. I've got a 3x and a 2x, which I believe is 5x, minus the number 7, right? That's what I get with the positive 5 and the negative 12. On the other side, I'm going to have a negative 4x and then a negative 1. The negative 1 is the result of combining negative 4 with positive 3. All right, let's add 4x to both sides. I get 9x minus 7 is a negative 1. And if I add 7 to both sides, I get that 9x is, what's that going to be? That's going to be positive 6. Yeah. Therefore, x is 6/9. And I know that does have a giant 1 of 3 over 3. So that's the same as 2/3. So I believe x is 2/3. Now I'm going to go ahead and check that, and why not demonstrate that here? You're here. This is our classroom calculator. Let me bring that up. There it is. And I think that x is 2/3, so I'm going to go ahead and enter 2/3. Right, and I'll just press enter there. It's 2/3. Now that I've got 2/3 on the stack, I'm going to store that in the variable x. Store x and then enter. At this point, my calculator believes that x is 2/3, right? If I say, hey, what's x? It says 2/3. If I say, well, what's 2x? It's going to say 4/3. Okay, that's interesting. What about 3x? 3x, it'll say 9/3, right? 9/3? Wait a minute. 3x, 2/3, that would be 6, right? 3 times 2/3 would be 6/3, and 6 divided by 3 is 2. That's beautiful. All right, so we know what x is. X is 2/3. Is it the solution? Well, that's a fair question. It's a solution if it makes the left and the right-hand side the same, right? This whole expression over here, the 3x plus 5 plus 2 times the quantity of 2 times x minus 6 rather, has to be the same as this side. And to verify that, it's not too taxing. I just type the 3x, got it. I hit plus 5, got it. Plus 2, yeah, open paren. And then I'm going to have an x and a minus 6. And I just look at it, verify 3x plus 5 plus 2 times, yeah. When I press enter, it says that, my friends, is negative, I'll write it right here, it's negative, I get negative 11 over 3. I don't have to write it down, it's going to stay on the calculator screen. Let's look at the other side. All right, the other side is just going to be 3 minus, oops, wrong calculator, 3 minus 4, open paren, x plus 1, close paren. And guess what? 3 minus 4 times the quantity of x plus 1 is exactly negative 11/3. Well, guess what? Guess what? If x is 2/3. It makes both sides of this equation's negative 11/3. It makes them truly equal to each other. So this is a solution, and I can circle it, and I can put a happy face next to it. Let's go to the next question. This next question has this binomial multiplication going on. And for now, I like demonstrating using a generic area model to just practice multiplying this. So what do I have here? I have a binomial x plus 3 times the binomial 2x plus 1. When I multiply those, I get a 2x squared, I get an x, I get a 6 times x, and I get the number 3. So that left-hand side is the same as 2x squared plus 7x plus, oh, no, this was a -1. Oh, I made a mistake. Let's fix that before I go much further. Okay, because this is a -1, I'm glad I caught that now. Although I would have caught it when my answer didn't work. So this is a -1, so I've got a 2x minus 1 and an x plus 3. This should be a negative x, and this should be a -3. So when I combine these, I've got 2x squared plus 5x. What's that? That's 6x minus one of them, right? So this will give me 5. And then I've got minus the number 3. On the other side, I've got a 2x squared plus 12. Now, conveniently, both of them have exactly a 2x squared. So I'm going to subtract that term from both sides, take it away from both sides. And I'm left with this equation, 5x minus 3 is 12. Therefore, 5x is 15. And I believe x should be 15 fifths. X should be 15 fifths. 15 over 5, 15 fifths. It should be 3. So again, it says verify that this is indeed a solution. So we've got the calculator here. Might as well use it. I'm going to change what x is. Before it was 2/3. I don't want it to be that anymore. I want it to be 3. So I got 3 on the stack. And I'm going to hit store x. Now my calculator believes x is 3. And if I hit x squared, it's going to say 9. If I say 5x, it's going to say 15, right? So you can see that's all dialed in. Let's look at the original problem. So we had open paren, and then we had an x plus 3, x plus a 3, and we were multiplying that by an x, by a 2x, and then a -1. Perfect. When that side is evaluated, it becomes 30. On the other side, I've got a 2x to the second power, and then I have plus 12, and that is exactly 30 as well. So when x is 3, the left-hand side is indeed equal to the right-hand side. So x is 3 is most definitely a solution to this equation. Let's move on to question 3. Question 3 had 3 different problems for us to solve. And it mentions here, looking inside and fraction busters may be useful strategies. So let's not forget those. So let's take a look at the first one, right? So as I look at this, my first thought is, look, I'm taking the square root of some quantity and I'm getting an answer of 8. I know that this thing inside, right, this value has to be 64, right? So my solution process is pretty straightforward. I say, look, if I can make 12x plus 4 the same as the number 64, it's going to work. Why, you say? Well, because I understand that the square root of 64 would give me the desired 8, right? It would give me the 8. So what do? Well, I'm going to subtract 4 from both sides. So I get that 12x is the number 60. And then x, therefore, is 60 over 12, 60 twelfths. And I think that's the same as the number 5, right? 5 times 12 is 60. Yeah, so x is the number 5. And I'm not gonna use my calculator for this, but just real quickly, I'm inspecting. 12 times 5 is 60. 60 plus 4 is 64. The square root of 64 is 8. It's absolutely the solution. X is equal to 5. Next one. So this is the looking inside or rewriting that's a little complicated, right? So I need these two. This is an exponential equation. I call it that because my variable lives in the exponent. And I need to rewrite this so that the exponent, so that I can solve x. The strategy we've talked about in class does not involve logarithms, right? It involves rewriting it so that the bases are the same. And looking at this, I know that the 49, right, I can rewrite that as 7 squared. So when I see 49 and 7, when I see this 7 and this 49, I'm thinking, hey, how can I get the same base? Well, this is my strategy. 49 is the same thing as 7. Now, I'm not done yet because the bases are still not both 7, right? So what I do now is I go ahead and use the rule a power raised to a power. So I've got 7 squared, and I'm going to raise that to the 2x minus 1 power. So we know that if I have a power, this is from the whiteboard, blue cabinet, if I have a power like x to the m, and I raise that to the n power, that's the same as x to the m times n. So I'm just going to multiply the 2 times the quantity of 2x minus 1. And I get that that's the same as 7 raised to the 4x minus 2 power. And I'll just bring down the other side here. This is equal to 7 to the x plus 2 power. Now, because my bases are both the number 7, right? This is 7 raised to something, 7 raised to a number. The only way that's true is if these exponents are equal to each other. So our strategy now is to set the exponents equal, right? So I'm going to say 4x minus 2 must be the same thing as x plus 2. Therefore, 3x minus 2 must be the same thing as 2. Therefore, 3x must be the same thing as 4. So x has to be 4/3. So I think x is 4/3. That's what x is. It's 4/3. How do I... this one, I think I feel the need to check it. So let me bring my calculator back up here. Where are you at? There you are, calculator. And if I check this again, same things. I'm going to enter 4/3, so 4 fraction key 3, and then I always press enter. It just works better for me. And then I store that in x. My calculator believes what I told it. I told it x is 4/3, and it says, yeah, x is 4/3. All right, so what is 49 raised to the power of 2x minus 1? You can see that's exactly what's on my page, right? 49 raised to the 2x minus 1. It says this. Ooh, what about the other side? Okay, let's say 7 raised to the power of x plus 2. What's that? They are both exactly 656.1353. There we go, right? This value of x makes both the left-hand side and the right-hand side the same. So it's a solution. Rewrote the base so that they were the same and moved on. Next problem, C. Okay, C. This strategy we talked about is fraction busters. It may be useful. As I look across here, I can see that my denominator has a factor of x. This denominator has a factor of 2, and this one has a factor of 2. It turns out, putting that all together, that 2x would be the perfect fraction buster. 2x would bust all those fractions up. So I'm going to multiply each one of those fractions by 2x. And I'm going to show this step, right? It's going to be 3 times you get a 2x, right? Plus 5 times you get a 2x. And that equals 7 times you get a 2x. So guess what? Everyone just got a 2x, right? I hit every single term on both the left-hand and the right-hand side with 2 times x. Now, I can simplify this quite a bit, right? You can see this is a giant 1. This is a giant 1. And this is a giant 1. Okay, so what does this become? Well, the first term is going to be the number 6. And then I'm going to have plus 5x. And I'm going to have equals 7x. Okay, that means that 6 is the same thing as, let's see, 7 minus 5x is 2x. Therefore, x is 6 halves. X is 6 halves. I'm dividing both sides by 2. Divide by 2. X is 6 halves. Therefore, 3 is what x is. And again, because of the nature of this, and this is a fairly new type of problem for me, let's clear this. Just go ahead and say 3 is x. And if it's not a fraction, I'll just do that. 3 is x. Boom, x is 3. Let's compare. So I've got 3 over 3. That's going to be fun. 3 over x, which is 1, plus 5 halves. Boom, ba-doom, ba-doom, boom. And this has to be the same thing as 7 halves, and you can see it is, right? So clearly, when x is 3, it makes both sides of the original equation 7 halves. X equals 3 is the solution. All right, let's move on to our second page. For our second page, we're supposed to plot some vertices and then do some transformation. So a challenge is always getting these points plotted correctly. So my first point is at 7, 7, -3. So I'll go ahead and grab this pen, and I'm going to plot a point. No, I'll keep the color the same. So I've got -7, +3 as a point, and that is the point A. The next point that I have is -6, +2, and that is B. And then my third point is -4, -4, comma 4. -4, comma 4, which is C. So you can see I've got triangle ABC. I can connect these points. Here's my original triangle, and I'm going to subject it to some transformations. First, it says take that wonderful triangle ABC and reflect it across the x-axis and create a new triangle and label it A prime, B prime, C prime. So again, here is my x-axis. Let me get rid of this calculator. Doop. Here's the x-axis. I'm going to be reflecting across this. Right, this is x. And when I do that, this point is going to just, it's 2 above, it's going to become 2 below. So this is going to be B prime. It's 3 above, it's going to become 1, 2, 3 below. This is going to become A prime. And then this is 4 above, it's going to go 4 below. This is going to become C prime. So that reflection is pretty straightforward, right? Because I know that when I reflect across a line, the distances of the original shape to the images have to be equal. And my line of reflection there is the x-axis. Next, it says take this thing and rotate it 180 degrees around the origin and label the new triangle. So we can do this a couple of different ways, but in my mind, you know, I can see this is what I'm rotating around, and I can see that C is going to lead the way, right? And B is going to follow, and A is going to be following. And when I do this, when I rotate C all the way around, it's going to end up, right? It's going to end up at +4, +4. So here's one of the things that's really cool about a rotation of 180 degrees. If you rotate something, if you've got a point X, Y, and you want to rotate it 180 degrees, all it does is it goes to the opposite of the X and the opposite of the Y. Now, visually, I can see this, but this rule I'm thinking about because I've encountered it. You don't have to memorize anything like that. Do this however you want. I just try to notice these things when they're happening. So C is going to go to +4, +4. B is going to go to +6, +2, +6. So this is going to be where B, by the way, this is now B double prime. This is C double prime. And the last one, A, is going to go to, so you can see where A is. It's at -7, -3. It's going to go to +7, +3. So here's my new A double prime. And you can see it's, you know, this like if you imagine it like a ship, it's still facing the same direction, right? A and B are in the back of the ship, and C is like the front where it's pointing. And this is our now third transformation that we've subjected this to. And then finally it says we've done a reflection, we've done a rotation. Now it's asking us to do a translation by using this rule. And this rule says, look, whatever X and Y are, decrease X by 5. That's what this means. Decrease your X value by 5. So whatever X is, decrease it by 5. And whatever Y is, decrease the Y by 2. So if I'm looking at this, I'm just going to take this C and go 1, 2, 3, 4, 5, and then I'm going to go down 1, 2. So this should be my new C triple prime. So I've moved it to here. Same thing with the A. 1, 2, 3, 4, 5, and then down 1, 2. This is going to be my A triple prime. And then for B, 1, 2, 3, 4, 5, 1, 2. This is going to be my B triple prime. So I have the final iteration of this triangle after I subjected it to a translation. So we have a reflection, a rotation, and a translation. And then there's a couple checking points here. It says, what are the coordinates of C prime? I can see prime, C, it's right here. C prime is at -4, comma, -4. Those are its coordinates. What are the coordinates of B double prime? B double prime is living at 6, comma, 2. That's right here. That's B double prime. And then finally, what are the coordinates of A triple prime? Okay, A triple prime is apparently at 2, comma, 1. 2, comma, 1. That's that point right there. All right, so we've Then all three of those, and we identify some points. So we're now on to question number 5. Question 5 says, evaluate this expression if you have a value for A, for Y, and for Z. So look, I've made mistakes with problems like this a lot. And the strategy I use to avoid that now is I'm just going to say, look, here's 4 minus a place for X over 9 plus 3 raised to the power of a place for Y, and then plus 12 times a place for Z. So I didn't put any of the other numbers in. So A is -4 and Y is -2. So I've identified where the variables are, and then I've plugged in these numbers, right? And you can see that exactly A was plugged in where A was needed. Y was plugged in where Y is needed. And I've got this, I'll use this orange. And Z was plugged in where Z was needed. At this point, I'm just going to evaluate each of these 3 terms kind of carefully and see where that gets us. So this first term, 4 minus -4, looks like the number 8, right? So I've got 8/9. So I've got an 8 in the numerator, 8/9. And then I've got 3 raised to the -2nd power. Now, I know that that's the same as 1 over 3 to the 2nd power, or that's the same as 1/9. It's nice, you know, I might be learning these exponent rules, so might be nice to verify that. So if I throw my calculator on the screen, I could just verify, hey, 3 raised to the power of -2, and it does say 1/9. So 3 raised to the -2nd power is a 9. So I've got 8/9 plus 1/9, and then plus 12 times 6 is a half of 6, or it's the number, I'm sorry, 12 times 1/2. What am I saying? 12 times 1/2 is 6. I'm thinking of the answer. 12 times a half is 6. Half of 12 is 6, so I've got a 6 here. So what am I looking at? I'm looking at 9/9 plus 6, which is 1 plus 6. So my answer here, this expression is the number 7, and that's beautiful. I don't really encourage it because I think it's probably way more work than it's worth. But I do want to point out that these calculators would keep track of different variables. So you can see I've got X, Y, and Z, and I could store those, and there's other ones too. I could store those and then evaluate the expression, but I think it's more work than it's worth. Next, find the slope of a line that goes through 2 points. So I'm just needing the slope. I'll remind myself of a couple of things, right? This slope, right, is, and sometimes you use the variable m for it, is the change in our y values divided by the change in our x values. Or by the change in y, it's like, hey, what's y from one of the points minus y from the other? And then the change in x, what's x from one of the points minus x from the other? And then I like to write this down. So here's a place for y2 minus y1 over, here's a place for x2 minus x1. So I just kind of organize my work this way. I find that it helps me reduce errors, and I mean, you see me make mistakes. So let's clear this calculator out of the way for a minute. Okay, so let's plug in what we've got. So I'm arbitrarily gonna call this my first point, and I'm gonna call this my second point. And I can see that the y value at my second point is the number 150. The y value at my first point is 154. Also, I see that the x value at my second point is -8, and the x value at my first point is 12. Okay, so what am I looking at? I'm looking at the 150 minus 154 looks like -4. And then in my denominator, I've got, I believe, -8 minus 12, which is -20. So you can see both of those are negative, right? I've got -4 over -20. So it looks like my slope is going to reduce to, because both of those are divisible by 4, and a negative over a negative is positive. Let's not be sloppy. Let's look at this. So here's our -1 times a 4, okay, over, there's a -1 times a 4 times a 5. And what's happening here is I've got this -1 times 4 over -1 times 4, that's a giant 1. And I'm left with just 1 in the numerator and 5 in my denominator. Completely not recommended because, I need to see the work for partial credit to happen. But if you wanted to check that using your calculator, you could certainly, it'll handle it perfectly fine. So if I look at this calculator, I grab a fraction template, and in the numerator, I'm just going to do 150 minus 154. And then my denominator, I've got, -8. So if I need a negative number, use this, -8. And I'm going to subtract from that positive 12, and I get exactly positive 1/5. So slope is 1/5. Next question says, write these two numbers one in standard notation and one in scientific notation. So if I want to expand this to standard notation, right, you can see that I have to multiply by 4 factors of 10, right? So here's 1 factor of 10, 2, 3, and 4. So I'm just counting every single time I move the decimal over 1 or add a 0, right? That's equivalent to multiplying by 10. So this 32,000 is what this number is. For this other one, the decimal has to live here at 2.7. Now the question is, to turn this 2.7 into this number above, I've got to divide by a lot of 10s, right? It's got to become smaller. So to divide by 10, I want you to remember this, that 1 over 10 is the same as 10 to the -1. So I have the calculator in the way there, I'm sorry. 1 over 10, I wrote 1 over 10 is the same as 10 to the -1. So when I have a negative exponent, that's equivalent to dividing by 10. So if I divide by 10 once, right, what's that going to make it? That's going to make it 0.27. But I have to divide by a bunch of 10s. How many times? Well, I've got to do it 1, 2, 3, 4, 5 times. So I'm going to divide by the number 10 5 times, and I get 2.7 times 10 to the 5th. This is a weird situation because whenever we write numbers in scientific notation, we need to use this symbol, but it's tough because, there's X and then there's this, right? There's this. And I got to be careful because I do this pretty predictable X that's a little curvy like that. But this is just like multiplication. So this is 2.7 times 10 to the -5th. That's the notation we expect to see when we're using scientific notation. All right, let's move on to our third page. The third page says, and I quote, find the equation of a line that is perpendicular to this line and goes through or passes through the point where x is 12 and y is 9. Well, if I want perpendicular, I have to understand that this slope is 1/3. So for not 1/2, 1/3. So for perpendicular to this, right, the slope that I'm going to use is going to be the opposite reciprocal of that. So -3 over 1, or just -3 is going to be my slope. So I've got the slope, right? The slope is -3. I've got an x value and I've got a y value. That looks like I've got point slope. I can go two ways. I can plug this into the point slope form of an equation, or I can solve for b. I'll solve for b today. So I'll write, hey, y is mx plus b. The y value, the point it has to hit is 9. And my slope is -3. And my x value is 12 plus b. So what am I looking at? 9 is equal to -36 plus b. Okay, -36 plus b. So I have to add 36 to both sides. So 9 plus 36 is what b is. That is, b is 45. So I now know both pieces of information. I can write the equation of that line, right? The equation of the line is y's are equal to, my slope is -3, and then times x, and then I have to add 45. So a couple things that I can think about to check this answer. If I plug 12 in for x, when I plug in the number 12, y better come out as the number 9, right? I expect that because of this point. And the other thing that I can just visually see is this does have the correct slope. My original my given equation, right, had a slope of, over here, it had a slope of 1/3. So to be perpendicular to that, it has to be flipped. It has to be opposite in sign and the reciprocal. And I can see I've got that going on. So it looks pretty good. Next, graph the following equations on one set of axes. I think axes. Axis? I think I used the wrong word there. So let's graph both of these equations. So this first one has a y-intercept at 7. So I'm just going to count up. I'll use red for this one. I'm just going to count up. I'll go 1, 2, 3, 4, 5, 6, and 7. That's fun. And then I have a slope pattern of down 2 over 5. So I just go down 2 over 1, 2, 3, 4, 5. And why not do it again? 1, 2, 3, 4. No. 1 down 2 over 1, 2, 3, 4, 5. Good. Good. I need a ruler for that. And by the way, on a test, either use like an index card, ask for an index card. I've got some rulers, use a ruler, but use something, right? If you just kind of write some squiggly line on there that's not straight, that is not good. And I've been known to take off points for that. So that's a nice clear line. And I should also include these arrows, right? Because this continues forever in both directions. So that is the line. Y is negative 2/5 x plus 7. The other line that I have here is, well, it's not in slope-intercept form. It's in standard form. And I can do two things. I could figure out what my intercepts are, plot those, and connect them. Or I can just turn this into y-intercept form. And I'm going to choose the second one. I'm going to take away 2x from both sides, minus 2x. So this becomes 4 times y is negative 2x plus 12. And now if I just divide everything by 4, right, it's going to look just like this original problem up here. I'm going to graph this one in blue, though. Graph this one in blue. So my last thing I'm going to write is y is negative 2 over 4x plus 12 divided by 4 is 3. And oh yeah, that simplifies. Y is negative 1/2 times x plus 3. So I've got a y-intercept at 1, 2, and 3. And then I have this slope pattern of down 1 over 2, down 1 over 2, down 1 over 2. This looks a lot like the previous line, but I can see the slopes are not exactly the same. And eventually it looks like they're gonna intersect each other somewhere on the negative side of the x-axis, right? Okay, so now I've got those all lined up. You can see that's the red slope. This one's a little different. I have to tweak this slope. And now that I have that, I'm going to very carefully draw the line that goes through those and then extend it in both directions. All right, so that's what this should have looked like. You can see I've got the graphs of both of those. I did rewrite this equation in slope-intercept form so I could kind of easily graph that. Next, express the area of a rectangle below as the product of its dimensions equal to the sum of its parts. All right, so product of its dimensions. I need to know what the dimensions are, so let's look at it. Going up and down here, this is x units long. Right, this is x units long. From here to here is x tall. And then this is 1 and this is 1. Going the other direction, this is an x and this is an x. So this has 2 x's. And then it's got a 1, 2, and 3. 1, 2, and 3. So as a product of dimensions, what do I have? I've got x plus 2 times the quantity of, oops, not x, 2x. There's 2 x's across the top. 2x plus 3. And then, as the sum of the parts, I'm just going to look here. Inside of this, I can see I've got 2x squareds. So I write 2x squareds. I've got 3x's plus 4x's, so I've got plus 7x's. And then what's this? That's the number 6 plus 6. So this is the area of the rectangle expressed two ways, and I show that they're equal to it. One is the product of the length times width. Product of length times width is equal to the sum of its parts. The sum of its parts. Question 11. Use the distributive property to find each product. Use a generic area model to organize your work if needed. Well, I definitely do not need that for this first one because this is the simplest form of the distributive property. I'm just going to multiply each of these terms, right? I've got a term of an x and a term of a negative 3. I'm going to multiply each of those by 4x. So when I multiply, I'm going to have 4x squared minus 12x. That's 4x times x is 4x squared, and then 4x times negative 3 is 12x. Excellent. This next one, I am going to definitely organize my work, and I recommend it. A lot of you made some mistakes, right? So I'm going to start by I'm going to start by drawing a rectangle there, and across the top, I'm going to have 3 terms by 3 terms. So I'm going to go 3 this way, and then 3 things this way. And I'm just going to write these down. From top to bottom, I'll use this one first. I've got an A plus a B plus a 2. So that's, no, plus a, I had to turn that off because this is gone. A plus B plus 2. And then across the top, I've got an A. And then I've got a negative 2B. And then I've got a 1. Okay. So I need to find the area of each of these little tiny rectangles in this generic area model. The first box up here is a times a, so that yields a squared. Below that, I've got b times a. And below that, I've got 2a. All right. Next column, I've got a times negative 2b. I'm going to write that as negative b times a. No, there's a 2 there. Get it right, Roberts. That's going to be negative 2, and I'll put the a here. Negative, let's keep this consistent. Negative 2 times b times an a. Below that, I'm going to have negative 2b and squared. And below that, I'm going to have negative 4 and a b, negative 4b. And then my last column there, I've got a times 1 is a, b times 1 is b, and 2 times 1 is a 2. So some of these can be combined, right? I'll highlight these. So this one right here, these are both ba, and then I've got negative 2ba. So those can be combined with each other. Other things that can be combined, I've got a 2a and an a here, so those should be combined. And the other thing I see that can be combined is that there's a negative 4b and there's a b. So those are like terms. And when I write down my final product, right, what do I have? Well, there's an a squared, okay, a squared, check. There is a negative 2b squared, all right, negative 2 and b squared, check. When I combine the blue ones, I'm going to have just a negative BA minus BA. You can write AB too. That doesn't matter. But there has to be a negative. So I've got minus 2BA plus a BA, which makes negative 1BA. Yeah, these are gone. Check. If I combine 2A and A, that's going to be a plus 3A. They're taken care of. And then I've got a negative 4B and a positive B, which is going to look like negative 3b. Okay, you guys are gone. And the last thing I have is a plus 2. So this, right, should be the product, the simplified product, when I multiply that trinomial times a trinomial. It takes, it takes some practice, and it's a little tedious, but go slow. Look at what you've got carefully. Not the easiest thing to check, right, to verify that your answer is correct. So just go careful with it. All right, I'm going to pause for a minute. We'll pick up and finish this video in part 2. Okay, let's wrap this up. We are on the last page. The first question on the last page has a collection of algebra tiles, and it says the following figure was created with x squared, x, and unit algebra tiles. What is the perimeter of this shape? Okay, so if we have an x squared tile, right, we understand its dimensions are x by x, right? It's x times x that gives me x squared. So these lengths, right, from here to here are all x units long. So I've got an x. This is a 1, 1, 1, 1, 1, 1. This is special, right? Let me make this blue. This, I was going to make it blue. This is not 1, right? That length, if you look at it, there's an x tile touching it. And from that x tile, I'm taking away 1, 2, right? It's x units long minus a 1 minus a 1. So this is x minus 2 units. That's what this piece is. Then we continue with a 1, a 1. This is an x. That's a 1, that's a 1. This is another special piece, right? This piece right here is not 2, right? This is an x tile. except we took away 1 unit from it, right? This was subtracted from it. So it's an x minus 1. And then we continue on. There's a 1, a 1, a 1. This is 1, and this is 1. So if I look at this, there's quite a few like terms. I can see that I've got, I'll just circle these in orange. I've got 1, 2, 3, 4, 5, 6. I've got 6 x tiles. So part of my perimeter, right, is 6 x lengths. I'm sorry, 6x lengths, the lengths of x. But I got some more, right? I've got some unit tiles, and on these, let me circle these with this blue. I've got 1, 2, 3, 4, 5, 6, but I have to take away 2. I'll hold that on to the end. 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So there's 15 there, plus 15. But there's some negative that I have to deal with, right? There's a -2 and a -1. So I have to subtract 3 from that. So what it looks like the perimeter is 6x plus 12. So the length, if I was to start here and walk all the way around it, I would walk an x tile, some 1s, more 1s, more 1s, more 1s, an x minus 2, 1, 1, x, 1, 1, x minus 1, 1, 1, 1, 1, 1, and then finally an x. And that is the perimeter of that shape, the distance all the way around it. On to question 13. It says, graph the following equation. Label the line with its equation, the y-intercept, and a slope triangle. So this is not written in slope-intercept form. So I can go one of two ways with this. I can divide everything by 5, and that's probably the most reasonable thing. That'll give me y is equal to -3/5 x, and then plus the number 2. Okay, actually, let's do this. I'm not going to write it in standard form or anything. Let's just go this slope-intercept form. So I've got a y-intercept at 2, right? If I put 0 into this equation, it gives me 2. And it has a slope pattern of down 3, 1, 2, 3, over 1, 2, 3, 4, 5. So if I was to put 5 into this equation, it would say -1, and I can see that, right? If x is 5, that would give me an answer of -1. Down 3, 1, 2, 3, over 1, 2, 3, 4, and 5. If I was to put 10 into this equation, let's see, 10 divided by 5. 10 divided by 5 is 2. That's -6 plus 2 would be -4. That's brilliant. Yeah, that's exactly what's going on. Let me grab a ruler. Guys, use an index card, use a ruler, use the edge of your calculator case, use something to draw some straight lines. So this is a straight line, very intentional straight line. I'm putting arrows at the end of each side of this line because this is a function. If this goes on forever, it'll continue to do this. It's a line. It's not a line segment. So its equation, label it. Okay, so I'm going to label the equation. This is the line y is equal to -3/5 x plus 2. There's the equation. The y-intercept is right here. I'm going to label this. This is the point. X is 0. Y is 2. And then finally a slope triangle. I'll put this one right here. So I'm going to go, this is down 3 units. And then it's over to the right 1, 2, 3, 4, 5, 5 units. There's a slope triangle. So that's everything that was required for this problem. I believe we are on to our last problem. The last problem says, find the input values that produce the given outputs, or find the outputs for the given input. So the first case is find the output, right? Find the output when you know what the input is. And this over here, this is find the input when you know what the output is. So let's come up here and look at this. So I always, right, will take the time There's a place for x. I'm going to square that, plus 4 times, here's a place for x. My value of x is -3. I'm going to place a -3 in these two locations, so -3, and over here I have another -3. When I take and I square -3 times -3 is +9, plus 4 times -3 is going to be a -12, right? This is 9 plus -12, or 9 minus 12. And I believe, that's interesting, that 9, 10, 11, 12, it is -3. So when the input is -3, the output is the same. The output is -3. Okay, last question. Last part of last question. Here's the definition of a function. This function takes 1/4 of the input, and then it adds 80 to it. And I want to know what value do I put into this function so that I get an output of 120. In other words, this is the definition of the function 1/4 x plus 80. That does not look like a good 1/4. That's better. 1/4 x plus 80 has to equal 120. So I'm going to begin by subtracting 80 from each side. So 1/4 x equals 40. 80, yep, it's 40. And then to finish, I'm going to multiply both sides by the number 4. That'll create a giant 1, 4/4 on this side, and leave me just plain old x. And 4 times 40 is 160. So if I place 160 as the input for this function, right, it will give me an answer of 140. And yeah, I can see if this lands in here, right, 1/4 of 160 is going to be 40, and 40 plus 80 is indeed 120. So that is it. If you have any questions, like to discuss any of these, please stop by and talk to me. I'm in room, what is this room? Room 309. And I'm always happy to talk to you. Also, whoa, where'd my camera go? Oh, well, I'm not going to say goodbye. So stop by and say hi if you've got questions. This is Mr. Roberts. I'll talk to you soon.